and we have on page 210, okay, and now we have by definition, okay, we have an odd function, okay, is going to have symmetry with respect to the origin, and it is defined by the relation whereupon, again, we're going to have opposite sign inputs will lead to opposite sign outputs, and we have the f of negative x is equal to the opposite sign of f of x. Whereas in the case of even functions, okay, now the graph of an even function is going to have symmetry with respect to the y-axis. And we have that f of negative x is equal to f of x. So at same sign, okay, inputs, okay, or I should say same sign outputs, you have resulting from opposite sign inputs in the case of an even function. And for what we have on page 210, okay, now we're looking at determining whether the following function is odd or even for what we have in the case of number 34. So we have in 34, okay, so we have our function given in the form of p of x, and we have that p of x is equal to the negative of the absolute value of x plus 12 times x to the 10th plus 5. Okay, all right. So for what we have here, okay, so you got your p of x, and we're going to see how things look in the case of p of negative x. Okay, so we got in the setup. Okay, so this is what we have for p of x. Now for p of negative x, okay, so we got the negative of the absolute value of negative x, and we have plus 12 times the 10th order of negative x, followed by the addition of 5, and we have in the follow through. Okay, now the absolute value of negative x, now that is going to be positive x, and negative x to the 10th, okay, that is just going to be positive x to the 10th. And I'm still going to be taking the opposite sign of the absolute value of negative x, so I'm going to have, in this case, so I'm going to have negative x plus 12 times x to the 10th, followed by the addition of 5. Okay. And for the negative of the absolute value of x, now again, the absolute value of x is still going to be x, and I'm still going to be taking the opposite sign of this. Okay, so we have negative x plus 12 times x to the 10th, followed by the addition of 5. And if you notice, okay, we have from the very start, okay, so we have for x and negative x, okay, these are opposite sign. And in the case of the output, okay, notice we have negative x, 12x to the 10th, and positive 5 for both. And so we have unanimously, okay, all the terms will be the same throughout. Okay, so if we have opposite sign inputs leading to the very same output, this is going to signal that for what we have for p of x in this instance, that is going to be a case of what we have with an even function. So 34, okay, that is going to be an even function. Now, for what we have in the case of number 35, okay, so we have our function given as k of x, and here we have k of x is equal to, we have 13x cubed plus 12x. And seeing just how that is going to turn out, okay, if we have the input to be negative x. All right, so we have, again, going from k of x to k of negative x. So we have k of negative x, so we have 13 times, so that's going to be the cube of negative x, Then we have plus 12 times negative x. Okay. Now, for what we have in the case of the cube of negative x, again, this is going to be minus x cubed. All right. And we have in the follow through, okay, so we have negative, what's going to be negative 13x cubed minus 12x. Whereas in the function before, okay, I had 13x cubed plus 12x. And it should be negative 13x cubed minus 12x. Okay, now, again, we have in terms of the inputs, again, we're working with, again, opposite signs. And for what we have for the outputs here, okay, so we have 13 and negative 13, 12, x and negative 12x. And if we have opposite sign inputs to lead to opposite sign outputs, that means here that for this particular function, that one is going to be odd. Okay. Again, so if we had the same output, the function is even, as was the case with p of x and 34. But if you have opposite outputs as an opposite sign outputs throughout, okay, then the function is going to be one that is odd. Okay, now, in the case of what we have for number 37, okay, so we have our function n of x is equal to the square root of 16 minus, okay, we have the square of x minus 3, okay. And just for what we have in the case of n of x, okay, so if I were to display what I have here in expanded form, so we have for n of x, so I have 16 minus the square of x minus 3. Okay, so I have inside this radical, and I'll just go ahead and square this binomial, so we have 16 minus, and for x minus 3 squared, okay, so this will be x squared minus 6x plus 9. And if I go ahead and combine like terms together, okay, so we have 16 minus 9, which will be 7, and we have minus x squared, and subtraction over negative 6, okay, so that will change over to the addition of 6x. Okay, so we have, so here we have 7 minus x squared plus 6x. Now for n of negative x, okay, so we have 16 minus, and here we're going to put in negative x as opposed to x. Now just mention, okay, so for negative x minus 3 squared, we have negative x minus 3 times itself, and just foiling out, okay, so you have negative x times itself is x squared, then we have plus 3x plus 3x, and followed by the addition of 9, so we come out to x squared plus 6x plus 9. Okay, so we have in the follow through, okay, for n of negative x. So again, I'm going to have 16 minus the quantity of x squared plus 6x plus 9. And so looking at distributing, okay, so we have 16 minus 9, so we got 7. And we got minus x squared. However, for the variable term, we have a minus 6x. Okay, and so for what we have here, okay, it's going to be a little bit of static creating. Now both of these, okay, have positive square root terms. Now for for 7 and 7, okay, these are the same. And you got negative x squared and negative x squared. Those are the same. However, for 6x and negative 6x, okay, those are opposite. And technically, if you wanted to stress the sign values, okay, so again, we had positive radical terms. So those had the same sign. So it looked like with both radicals being positive, 7 being positive, negative x squared being positive, it was on its way to potentially becoming an even function. But because we don't have unanimously 6x or negative 6x for both of these terms with an opposite, okay, there's a bit of a scramble that is created. And so since you don't have unanimously the same throughout, but you have an opposite, so if you don't have unanimously the same or unanimously the opposite, this turns out to be neither even nor odd. Okay, and now for what we have in the case of 41, for 41, okay, so you have h of x is equal to 5x. Okay, so you have h of x is equal to 5x. And for h of negative x, we have 5 times negative x. And that is equal to negative 5x. Okay. All right. Now I'm just repeating what we have for h of x. Okay, so we have opposite sign inputs, and for the outputs, okay, we have only single terms, and those are also opposite each other. So if opposite sign inputs lead to opposite sign outputs, it's going to follow that for what we have for h of x equal to 5x. Okay, this is going to turn out to be an odd function. Okay, and just and we'll get into the piecewise defined functions in a moment, but just to kind of give you a bit of a visual. See, for what we have in the case of Desmos. Okay, so you have, like, for 34, okay, so you have y is equal to the negative of the absolute value of x, and we've got plus 12 times x to the 10th, followed by the addition of 5. Okay, if you notice, okay, now this is going to be an even function because you have symmetry with respect to the y-axis. So if you notice, to the left and to the right of the y-axis, okay, we have the sets of points, okay, we have equal distance from the y-axis and also on the same level. And again, just for even functions, and just taking what we have in the sample, okay, so again, you're going to have opposite sign inputs to lead to the same output. So you have like negative 116, positive 116. Negative 2, 12, 291, positive 2, 12, 291. So opposite sign inputs lead to the very same outputs. And for what we have in the case of, what we have for the second, okay, we had like 13x cubed plus 12x. And again, this graph is going to have symmetry with respect to the origin. And this would be a case of where, okay, if the function is odd, you're going to have this time, instead of the same outputs, we're going to have additive inverses in the output. So you have opposite sign inputs lead to opposite sign outputs. Here you have negative 1, negative 25, 125, negative 2, negative 128, and 2, 128. So that's the case of an odd function. And then we had with third case, okay, that which did not qualify. Okay, and we had the square root of 16 minus the square of x minus 3. Notice you don't have symmetry with respect to the y-axis or to the origin. And again, just yeah, so you got negative 1, 0. And if you notice, okay, had this been an odd function, opposite sign inputs will lead to opposite sign outputs. If you had an even function, we would have opposite sign inputs leading to the same outputs. And notice we don't have either case going on. Okay, so again, number 37 was a case of a function that is neither odd nor even. And for what we have, say with number 41, okay, we have with y is equal to 5x. Okay, so this is going to have symmetry and it's going to run through the origin. And just for what we have here, so you got 0, and we got negative 1, negative 5. And this is going to be a case of an odd function. So we're going to anticipate that once we have x at 1, y is going to be at 5. And we had just negative 2, negative 10 to flash. If I throw in 2, again, opposite sign inputs lead to opposite sign outputs. So y equals 5x, or h of x equals 5x. That is going to be a case of what we have with an odd function. All right. Now a while back we did look into piecewise defined functions. And so now just for what we have in this instance case, so we have with 47. Okay, so again, a piecewise defined function is going to be broken up into separate sections. And here we have f of x is equal to negative 3x plus 7. And it'll be for those values of x, okay, that will be less than negative 1. And then we have f of x is equal to x squared plus 3. And we have for negative 1 is less than or equal to x, which in turn is going to be less than 4. And then we have f of x is equal to just 5. Okay, for those values of x greater than or equal to 4. Okay, and so we have, and looking at the different inputs here, okay, so we're looking for f of 3, f of negative 2, and we have f of negative 1, and also we have f of 4 and f of 5. Okay, so for what we have for each of the inputs, what's in parentheses, we have in reference to x. Now for f of 3, okay, now if you look at plugging in 3 for x, now 3 is less than negative 1, that is not a true statement. Now for 3 for x, okay, negative 1 is less than or equal to 3, yeah, negative 1 is less than 3, and in turn 3 is less than 4, okay. So we have for this statement, okay, so we have the second inequality to apply. Okay, and in terms of the follow-through, in terms of what do I do with that value, well, I'm going to take the square of it and add 3. Okay, so we have 3 squared is going to be at 9. And we have in turn 9 plus 3 is equal to 12. Now for negative 2, now negative 2 is less than negative 1. So I'm going to be referencing that particular inequality. And so I'm going to apply the first part of the piecewise defined function where we have -3 times the input, which we have at -2, followed by the addition of 7. And here we have -3 times -2 is 6. And 6 plus 7, okay, is equal to 13. Okay. Now for f of -1, now -1 cannot be less than itself, so the first inequality does not apply. Now if I situate -1 in the compound inequality, now -1 cannot be less than itself, but it is nonetheless equal to itself. And then in turn, -1 is less than 4. Okay. So again, I was able to apply the compound inequality for the first input because -1 is less than 3. And here, on the basis that -1 is equal to itself, I'm still applying the second inequality statement. -1 is less than or equal to x is less than 4. So I'm going to be looking at x squared plus 3 once again. And with x at -1, so I have -1 squared plus 3. And the square of -1 comes out to 1. And 1 plus 3 is equal to 4. And for f of 4, okay, now looking at 4, okay, notice 4 appears twice in the inequality expositions. Now for 4 at x, now -1 is less than 4, but 4 in turn cannot be less than itself. And we have for the last of the inequality statements, now 4 is not greater than itself, but it is equal to itself. So we have for 4 is greater than or equal to 4. Okay, and so we have here we'll have in the follow through. Okay, so for the values of the input greater than or equal to 4, we have f of 4 is equal to 5. And then for 5 as the input, 5 is greater than 4. And guess what? For any inputs greater than or equal to 4, you're going to have your f of x. Okay, it's just going to be once again the constant value of 5. Okay, so that is what we're going to have in the case of the results for these respective inputs. Now for what we have in the case of, so for the piecewise defined function in 48, okay, now we have in the case of g of x, so we have g of x is equal to, for the first part, we have -2 times the absolute value of x, followed by the subtraction of 3, okay, for those values of x less than or equal to -2. And then we have next, okay, so g of x is equal to 5x plus 6. Okay, for those values of x such that -2 is less than x is less than 3. And then we have g of x is equal to 4. And it'll be for those values of x that will be greater than or equal to 3. Okay, and so we have, looking at what we have among the inputs. Okay, so I have g of -3, g of 3. And we have, looking for g of -2. Along with g of 0, as well as g of 4. And in terms of which portions to apply, okay, now for -3 is the input. We got -3 is less than or equal to -2. So that part with the less than makes the first inequality true. And we have next line for g of 3. Now 3 is not greater than itself, but it is equal to 3. So you have 3 greater than or equal to 3. And for g of -2, now -2 is not less than itself, but it is equal to itself. So we're going to apply for the set of values x such that x is less than or equal to -2, and for 0, 0 is between -2 and 3. And for the input value of 4, we have that 4 is greater than or equal to 3. And it's the greater than part that makes it true. All right, so we have for g of -3. Okay, so we have, this applies to the first case. So we're going to have -2 times the absolute value of -3 minus 3. And for here, okay, now the absolute value of -3, again, that is going to be a positive 3. So we're going to have -2 times 3, followed by the subtraction of 3. And -2 times 3 is -6. And -6 minus 3 is equal to -9. Okay. And for g of 3, okay, so 3, again, belongs to the last inequality. And only thing we do here is that for those values of x from 3 inclusive on up, okay, that is going to be equal to 4. Now for g of -2, okay, this is in reference to the first inequality, and we're back to the first part of the piecewise defined function. So you have -2 times the absolute value of -2, followed by the subtraction of 3. And again, we have the absolute value of -2 is a positive 2. And for what we have in following through, so we have -2 times 2 minus 3. -2 times 2 is -4 minus 3. And -4 minus 3 comes out to -7. And as for 0, again, 0 is situated between -2 and 3. And so we apply 5x plus 6. And with x at 0. 5 times 0 is 0. And we have that 0 plus 6 is equal to 6. Okay. And for g of 4, okay, so g of 4, since 4 is among the values of x greater than or equal to 3, there's nothing that g of x is going to be equal to at that value except, okay, we're just back to the constant value of 4. Okay, so we got for the respective outputs, again, g of -3 is -9, g of 3 is 4, g of -2 is -7, g of 0 is 6, and for g of 4, okay, that is only equal to 4. And now, in the case of taking what we have with categories, now we have another representation of y we have in the form of t of x. So we have just utilizing once again the functional notation. Okay, so we have t of x. And for the categories we have here, okay, so we have, starting out with what we have at the lower end. Okay, so you have t of x is equal to x for those values of x such that 0 is less than x, which in turn is less than or equal to 1. And then we have t of x is equal to 2x for values of x such that 1 is less than x, which in turn is less than or equal to 2. And we have that t of x is equal to 3x for those values of x such that 2 is less than x, is less than or equal to 3. And then we have t of x is equal to 4 times x, and that will apply to those values of x where 3 is less than x, which in turn is less than or equal to 4. Okay. And if we have anything outside of the realm of any of these inequality statements, then we cannot apply t of x at all. Okay, so we have with the various inputs. Now the first one that is asked for is t of 1.99. Okay, so for 1.99, okay, so 1.99, okay, that's going to fall between 1 and 2. So we're going to have, again, We have 1 is less than 1.99, which in turn is less than or equal to 2. Okay, so 1 is less than 1.99, and 1.99 is less than 2. And so for what we're going to do with 1.99, we're going to take the functional part that matches, and that's going to be 2 times the input. So you have 2 times 1.99. And so this will come out to 3.98. Now, in the case of kind of going with the resulting output for yet another decimal input, now we're looking at t of 0.4. And 0.4, it is positive, and it happens to be less than 1. So we're going to have the first case to apply. So we do have that 0 is less than 0.4. And again, it is less than portion of the less than or equal to 1 part that we had this whole statement to ring true. So in terms of what to do with 0.4, well, 0.4 is going to be your x value. And so for those values of x that are positive and less than or equal to 1, okay, this just comes out to the value of the input. So we have it 0.4. And for what we have in the case of t of 3, for t of 3, okay, so if you notice, 3 appears twice among the inequalities, but where 3 belongs, we want there to be an equal sign. Okay, so the last case does not apply. So now 2 is less than 3, that is true. And for 3 less than or equal to itself, okay, what makes it true is the equal part. And so in terms of what to do with 3, well, we take the 3x part here. So we have 3 times 3, and so that is going to be equal to 9. Okay, and then we have rounding out. Okay, so you have t of 1. Okay, so for the input value of 1, okay, so 0 is less than 1, and 1 is less than or equal to 1 thanks to the equal to portion. So for t of 1, this will be referencing t of x is equal to x, so t of 1 is equal to 1. And as for what we have for t of 3.001, okay, and this is going to belong to the last inequality, so you have 3 is less than 3.001, and that in turn is going to be less than or equal to 4, thanks to the less than portion of the second half of the compound inequality. So for t of 3.001, okay, this will be the last case where we have 4 times the input. And so we're going to have here the output, we're going to have it 12.004. All right. And now, just some of the categories we have in the mix, okay, and this is going to be referencing what we have among the Alex items. I think it's in section 1.7, and we're going to have what we refer to as maxima and minima, and we have okay, so you have relative maxima and minima. For increasing and decreasing functions. It's kind of a long title, but again, there are categories, okay, that will have opposite motion. and essentially opposite locations as well. And let me give you just a case of what we have with what I'm referring to regarding maximum and minimum. And we'll say that we have it's like an XY coordinate system. Okay, so what I got here, so I have the x-axis, the y-axis, and I'm going to do a kind of a sketch here. Okay, and say that I have now I'll just put in some ordered pairs. Okay, let's say we have let's say I have negative 1, 1. Let's say we have 2, negative 3. So we have negative 3, negative 4. Let's see, we have 7, 4. Eight, 1. So I'm just assigning ordered pairs for sort of the peaks and the dips. Okay, so I have ordered pairs here. So I got negative 4, 2, negative 3, negative 4, negative 1, 1. Let's say I have 2, negative 3, 7, 4, and 8, 1. Okay, now just for what I have regarding relative maximum and minimum. So we have, first of all, okay, so if I were to determine the relative minimum for f of x. Okay, so this graph in blue, okay, this is what I have for f of x. Okay, and now just taking what we have for the relative minimum. Okay, those are going to be what you're going to have for the y values. Okay, whenever the graph takes a momentary dip. Okay, so if you notice, okay, reading from in order from left to right. Okay, so you have the graph to be increasing. Then we have after it reaches this peak, it starts to decrease. So this point here is going to be your first relative minimum, and so you're going to have your y value at negative 4. Then after this, okay, so you have going back up. Okay, and then you have going back down, so you have another point, okay, where you have bottoming out. Okay, so you have at 2, negative 3. So your next relative minimum, okay, it's going to be y is equal to negative 3. If you notice, you have another dipping point, so to speak, and that is going to be at y is equal to 1. So you have at that point 8, 1. So you have negative 4, negative 3, and also at 1. Okay, so just kind of nickname here. So those are going to be the dips. In other words, where a decrease is immediately followed by an increase. Okay, and then for the relative maximum, and just a little nickname for this, okay, those are going to be the peaks. And those are also going to be y values. Okay, so we have, so you have for the, so if you notice, you have an increase followed by a decrease. So you have a relative peak point here, and this is at y is equal to -2. And then again, we have going past the first relative minimum, and then we have going back up, followed by a decrease. So you have this next point, we have y is equal to 1. And guess what? Another peak point we have at 7.4. So your relative minima, okay, again, will be for these relative bottom points, and the relative maxima, okay, we have with these particular peaks, okay, and kind of like a little bit of a kind of a bad sawtooth pattern. Okay, so you have the upside of each tooth, okay, you have to be the relative maxima, and then we have the bottom layers, okay, we have in reference to the minimum. Okay, now for what we have, let's say, if I were to take like determining the values, and we'll say that we have, let's see what we got here. And this is where the x values will come in. Say if you're looking at determining the values or the intervals, where in this case we have f of x is going to be strictly increasing. Okay, now what I'm going to do here, okay, so you're just kind of duplicating this graph here. Okay, so determine the intervals, okay, upon which f of x is strictly increasing. And so if you notice here, okay, so you have, in other words, you're reading the order from left to right. Okay, so you have, notice you have rising, okay, from left to right here. Also have another increase from left to right, another increase, and yet another increase. And now we'll be using as much of the entire real number system as we can. Okay, so the intervals you're looking at going back to x. Okay, so we have here for the intervals where f of x is strictly increasing, and our interval notation will consist of parentheses only. So we have going from negative infinity, approaching but not including -4, okay, and we have for the next increase, okay, so you have from negative infinity approaching -4, and then we have going from -3 approaching -1. Okay, so you have from -3 to -1, and then we have with the next increase, you have going past 2 out towards 7. And then for the last strict increase, you have for those values of x that will be greater than 8. Okay, so again, you have those 4 sections where the graph of f of x is going to be strictly increasing. So you have from negative infinity to negative 4, then going past negative 3 approaching negative 1, then we have going past 2 approaching 7, and then we have going past 8 and running upward and outward continuously. And we'll say once again, just keeping the same function f of x, and let's say if we're looking at determine the intervals. So if I'm determining the intervals where f of x is strictly decreasing. Okay, so you still have the same graph. Okay, and where we have decreases, okay, so you have it. So again, you have reading in order from left to right, so you have the decrease, and you have another decrease, okay, in other words, drop from a peak or relative maximum to a relative minimum. We have another decrease here, so you got 3 decreases. And now for the intervals, okay, so you have running past negative 4 approaching 3, and then we have running past negative 1 approaching 2, then we have running past 7 approaching 8. And so for those intervals, so let's say we have 3 areas of where the strict decreasing is going to occur. So we have going past negative 4, approaching negative 3. We have going past negative 1, approaching 2, and also we have going past 7 and approaching but not including 8. Okay. So again, just for the relative minimum and maximum. Relative minima are going to be like your ordered pairs, where you have the relative dips. Okay, so those are going to be the y values, and the maxima will be like the relative peaks, without the motion tending to negative or positive infinity. So there's going to be again those y values, negative 2, 1, and 4. And again, just for the intervals, this is where you have your x values involved. Okay, for the strict increase, as well as what we have with the strict decreases. And tell you what, in terms of let me just mention, okay, say if I have another graph here. Okay, so for what we're going to have, let's see. And we'll say we have for our ordered pairs. Okay. So we have 1, 1. 4, 5. So we have 8, -2. 12, 3. And let's see. So you have -4, 6. And -8, 2. All right. And let's say if I were to determine the following. So you have the relative minimum. Where the minima occur. The relative maxima. Where the maxima occur. And also just rounding out, okay, so you have intervals of strict increase. And the intervals of strict decrease. Okay, so just for the next few moments, there are some added terms here. So let's see what we get for parts 1, 3, 5, and 6. Now I'll explain something about numbers 2 and 4. So let's see what we get for parts 1, 3, 5, and 6 in reference to what we have for this function f of x. So let's see what we get for the relative minima and maxima, and also the intervals where we had the function to be strictly increasing as well as decreasing. Okay, for this graph f of x, okay, so if we're looking at where the relative minima are going to occur, okay, and we have now for the relative minimum, okay, so you're going to be looking at the y values of concern. Okay, so again, you're looking at your points, okay, where they kind of dip. Okay, so for what we're going to have in the mix, okay, so we're looking at this ordered pair, and also this ordered pair. Okay, so for the relative minimum, whenever like something like Alex is asking for the relative minimum, it's asking for the y values. Okay, so here we got y is equal to 2. And you can just write it in numerical sequence like y is equal to 2, 1, and -2. But we got y is equal to 2, y is equal to 1. And also where we have it y is equal to -2. All right. And then this is where the Alex speak can get a little bit confusing. Okay, now we got the the relative minima at y is equal to 2, y is equal to 1, and y is equal to -2. And then got like this other part asking where the minima will occur. Okay, and when it's asking where it's going to occur, it's asking just for the x values that will correspond. Okay, so we have for where the minima will occur. Okay, for whenever we had y is equal to 2, we had x equal to -8. And for y is equal to 1, we had x also equal to 1. And where we have y is equal to -2, that occurred at x is equal to 8. Okay, so your relative minima you have at 2, 1, and -2 in y. And where the minima will occur, those are going to be the corresponding x values, which we have at -8, 1, and 8. And now for the relative maximum, okay, those are going to be the upper layers. Okay, see like what we have among the sawtooth patterns. Okay, so for your relative maxima, okay, those again will be the y values. Okay, so you have at y at 6, also y at 5, and also y at 3, and where the maxima will occur. Okay, so whenever we have y at 6, okay, x was at -4. And when y was at 5, we had x at 4. And when y was at 3, we had our x value, which was at 12. Okay, so if you're looking at just the values of the maxima and the minimum, it's asking just for the y values. And in terms of where those y values occur, it's just asking for the corresponding x coordinates. Okay, so again, you have -8 whenever we have 2, 1 whenever we have 1, and x is 8 whenever y is at -2. And then for the maximum, we got -4, 6, 4, 5, and 12, 3. Now, in terms of the motion, where we have increases and decreases. Okay, now for the intervals of strict increase. Okay, so we have an increase here, another increase. You have yet another increase. And for the intervals, you're looking at just the x values. And there will be no brackets in these. Okay. All right, so for increase, so we're going from between -8 and -4. Okay, so between -8 and -4. Let's have an increase between but not including 1 and 4. And then for the remaining increase, we have between 8 and 12. All right, so have first, second, and third strict increases. Okay, and those are going to be the expressions we have in interval notation. So we have between -8 and 4 for x. And also x we have between 1 and 4 and 8 and 12. And again, for motion like increase and decrease, you're going to maintain the use of parentheses. All right, and then where the decreases occur, okay. And so just looking at the x values. Okay, so we have for the first phase. Okay, so we have going between -infinity and -8. And then we have with the next decrease, okay, so you have going past -4, approaching but not including 1. And then we have going past 4, approaching 8. And then finally we have going past 12 and heading out to infinity. Okay, so those would be the intervals of what we have for strict decrease. All right. And now there is a little part, okay, that you might run into regarding Alex. Okay, so again, we have our relative minimum, maximum, as well as the intervals of strict increase, as well as those of decrease. Okay, and just kind of using this as a reference. Okay, there is another part here regarding the graphs of polynomial functions, and this will be what we have in the case of turning points. And for what we have in the case of turning points. Okay, and say we have for a polynomial function, okay, now the introduction is going to be a bit theoretical, but I'm just going to stress the first term in the mix. Okay, so you have a polynomial function of the form where we have f of x is equal to a of n x to the n plus a of n minus 1 x to the n minus 1. And just from the first term, okay, so we have n is going to be the degree of the function. Okay. Okay, so n is going to be the degree of the function. Okay, so for a polynomial function of the form, okay, in the highest order term we have a of n x to the n, where you have again n is going to be the degree of the function. Okay, the number of turning points. The number of turning points is going to be n minus 1. At most n minus 1. And I'll stress this, okay, it's going to be at most n minus 1. Okay, so for a polynomial function of this type, where n is going to be the degree of the function, the number of turning points will be at most n minus 1. Okay, and another way of phrasing this is that the degree of f of x the degree of f of x will be at least 1 higher than the number of turning points. Okay, and just kind of bringing it into focus. Okay, so we had for this recent function f of x, and let's see. go this. Okay, so in other words, like for the number of turning points, you're counting up all the dips and peaks all together. It's got 1, 2, 3, 4, 5, and 6. Okay, so you're going to have 6 turning points here. And the possible degree of f of x. Now again, the degree of f of x, the degree is always going to be more than the number of turning points. So the degree of f of x, it could be 7, it could be 9, 11, or possibly any other odd power that is greater. All right. So number of turning points will always be less than the degree itself, and just kind of just kind of a crude sketch, but just kind of and I'm going to put up the x or the y-axis to see it has something that's kind of truncating throughout. So for this f of x, okay, so if you notice, okay, we're going to have 9 turning points. And from this, okay, so we have with the degree of f of x. Now remember, okay, now the degree of f of x, okay, it's always going to be greater, at least one greater than the number of turning points. So f of x could be 10, 12, 14, or some other higher even number. Say what we have for this f of x. So your number of relative minima and maximum altogether. So here we're going to have 6 turning points. And for the degree of f of x, okay, so at least one greater than the number of turning points. So it could be 7, 9, 11, and if it's anything else, it's going to be a higher odd number. Okay, all right. So those are cases of what we have regarding turning points. Okay.